time series shows you when the energy of the earthquake or some other explosions is come to be recorded by this sensor. If you have an array of seismic stations, you can view it slightly differently. This is actually an event that happened in Drake Passage earlier this year. We can see this is how the station at the South Pole, QSPA, recording this earthquake. But you can also see other seismic stations in the southern hemisphere recording the same events. But the way those stations are deployed, they are not systematic. They are deployed by different countries, different projects. So it's really hard to see the pattern of this event. And particular to be noted for Antarctica, since this was happened earlier this year, there are a lot of stations are actually recording the event, but we couldn't get the data because those stations are not real time. The same event, right? The May event, if you look at the recordings from North America, you can begin to see some patterns. Particularly for this waveform, it's the green stations. But now you can begin to see the PP wave, SKS, those are how we seismologists name those phases, and the Rayleigh wave coming into the array, sweeping through the continent. And you can see how consistent, coherent the signal is across the continent, right? We can see this because the United States has invested a ton of money, like tens of millions of dollars, in maintaining, developing the seismic instrumentation network like this. This network is part of the stations belong to the network called US Array. In order to deploy that, it took the community about 10 years to sweep through the whole lower 48 states. And later it went to Alaska. Particularly for this array, not every stations are deployed at the same time, right? Some stations are deployed earlier, some stations are deployed later. But if you just look at multiple events from the same place, for example, in this case, go from in Mexico, and you can try to treat them as the same event and glue all the signal together. Now you can see even more bigger coherent signal sweeping across this continent. This is how the surface wave is basically traveling through a continental scale region. And this is basically after this array, this is the first time we can visualize how the waveform, it is revealing itself to ourselves. And then we can measure many of the characteristics of the Earth using this array, right? By tracking this waveform, we can do a lot of imaging, study the lithosphere architecture. I'm going to show you some of the research from this array later. But an array of seismometers, if it's deployed in a systematic fashion, we will see many things that we never imagined to see before. This is one of the reasons why when we look at the seismic deployment in continental Antarctica, there are individual program stations, they are deployed at the station, but there are also a lot of the networks that are deployed in places that earth scientists find it interesting, right? And all of those stations, they are not a single one. They are not just randomly thrown out. They are all deployed in a certain fashion, right? A notable array like TAM size, GAM size. GAM size is the one that came out from the last IPY, and as well as POLNet. And there are also arrays deployed by some audience here. Sam did do the TAM-NET. So since the last IPY, or more accurately, since the early 2000s, our community, the polar seismologist, has done a ton of work there in terms of developing and deploying, maintaining arrays of different seismometers on this continent, and we have learned a lot. Well, today I'm not going to go through individual studies coming out of them. We have heard a lot of the talks on those things. What I want to mention is each individual of those seismometers is not easy to put out, okay? This is a typical POLNet style seismometer. In order to do this, you need a seismometer, but you also need the power system. Then it includes the solar panel as well as batteries that can make sure it goes through the winter time. And in order to put this whole system out in the remote region, often we are going to use those twin otters. Okay, so think about this. If we are thinking about the US array type of things, in the United States, then you can see an earthquake, right? If we want to bring that capability to Antarctica, we have to use that airplane. I myself, I'm a more junior person, so I began to help with seismic deployment in Antarctica about 10 years ago. But I'm lucky enough to run a small network near the South Pole. Particularly, I was doing the similar thing. I put out those large broadband seismometer, about 9, near the South Pole. And when I was writing my proposal, I was trying to do the same thing. Give me a twin otter so I can fly there, put it out. But in the meanwhile, we also have some smaller instrumentations, which is on the right side, much cheaper. And they can be put out very easily. So I was thinking, I have about 150 of them. How about I put them between those stations? But apparently, you can guess, twin otter pilots, they wouldn't stop for me, right? So this brings to the capability that we were lucky to have in the past 2 seasons. We were working with this, those very, very capable trucks maintained and driven by the company called Arctic Trucks. What we did is, we as a NSF funded the project, we still have to go through NSF Office for Polar Program, but they directly contract the Arctic Trucks through their logistics side. And rented 2 trucks for 2 seasons for us. And in this case, we don't have to fly to a broadband station. We just drive there. Right? We can drive there, dig a hole, and bury it and leave. In this case, I don't have to hear the pilots telling us, hey, 4 hours, I have to fly, or the weather is bad, we cannot fly. And we can just do that. And if you are familiar with the US system, if you have done project with the US system, this perhaps will surprise you more, right? Every year before we do the field work, we do this initial planning and we set a date of when do we finish the work. If it was said January the 18th, you finish the work, usually you can assume like January the 28th, you can be back to McMurdo, right? In the first season, I decided to make a detailed log of what we were doing. Like every other project, we were delayed, right? The people were waiting in Punta Arenas, those truck drivers, because of bad weather, or we were waiting somewhere in Christchurch. So we were delayed at the beginning. That's normal. Everybody was expecting that. But after the seasons of work, every day either we are driving or we are preparing. At the end of the season, January the 13th, we were departing for New Zealand. And by the way, the planned date was January the 18th, 5 days ahead of time. Okay. This definitely make a lot of our logistic colleagues well satisfied how we can do this work. And it's more than that, right? Because then we are driving on the ice, so we can bring individual of those small nodes and put them out. I can just tell the truck, hey, stop in the next 2 kilometers. I'm gonna do a nodal deployment. And we just did do that. Maybe I can show you this is how we are doing the deployment. I was on this truck, driving through another truck, waiting for them to finish. The driver was doing some important biological procedure. And the team of 2 get the deployment done, right? 1 minute, you drop a station, you get it done. And because we were driving near the South Pole, there were tourists. They just camp out there, right? Some of them, they were just, hey, I want to walk to South Pole. How do I do that? And this is a team of them walking towards the South Pole. I think they were trying to experience, right, in the old days, how Scott is feeling the loneliness, the expedition. You can imagine how, when they see our trucks, what they were thinking. This is perhaps the last thing you would expect in a deep field. Anyway, so we did do this deployment. And our nodes, it does not need a external power. It has its own battery. Its battery would allow it to run like nominally 30 days. And during our first field trip, we made most of the nodes recorded for 25, 26 days. And we see clear earthquakes. And if we count how many earthquakes we see, we actually see a lot, right? Out of 60 earthquakes, and we believe we could see 50%, more than 50% of them give me very coherent signal. This is one of the examples. I'm comparing a node, this very small instrumentation, compared with the broadband, the one that you have to fly with a twin otter to deploy. This is one event. They show very similar signal when they are closely located and looking at the similar frequency band. And this is one event that we see along an array. I'm going to show you why this is important, but this is very, very coherent for a seismic array. And we see other things. For example, this is the noise level along for one station during the whole period, right? You see the more reddish color, it means more noisy, and the more white color, it means lower noise. You see how the South Pole station work during the day. Sometimes they make more noise, sometimes they go to sleep. Because we have the array, we can also see how this noise decay over distance, right? This is right end of the South Pole. During the daytime, the noise would travel much further away than the night noise, right? And this actually gives us very useful information if we are trying to deploy the very quiet seismic station. Actually, you shouldn't be close to South Pole. You should be at least 100 kilometers away from South Pole. So when our seismology colleagues are talking about QSPA, the South Pole station, being quiet, it can be even more quiet, right? So that's useful. And there are other useful things. This is another example. In seismology, we often look at the earthquake recording, and not every, for the same station, different earthquakes give you different signals. So we often ask ourselves, which one is better, which one is worse? Because every single time the wave travels through the earth, it gets some noise, right? For example, this is 2 events. One vertical component, horizontal component. Horizontal component is always noisier. When we try to study the structure beneath it, we are going to deconvolve some of their similar signal from the event. So this deconvolved function is shown up here. Some people call it transfer function, receiver function. if you look at those deconvolved functions, you may think, this is a good event, right? Because this is very similar to what you would expect from the receiver function that is generated from a simple ice plus rock model. That's what you would expect. So if I ask which one function makes more sense comparing with the synthetics, you would say the left side, no brainer. But if you look at the recording of the same event along the array, you quickly recognize that even for vertical component, this event is more noisier. Horizontal component is the same thing, more noisier. And this event just got beautifully recorded along that line. And as a result, the transfer functions, the receiver function from single event on this plot, you see how it coherently changes with distance, while another one has just less signal for us to interpret, right? Imagine if you only have two broadband, that is 90 kilometers from each other. You really cannot see the coherence because it's just too far away for you for us to be very difficult to decide whether it's from the real structure or it's from the noise. But now we can do that. So apparently with this dense deployment, we see a lot of advantages. We can do quick deployment. We can apply array processing techniques. I'm not going into the details of the things. Potentially we can get more higher resolution structural maps. And it also provides a way to perform the consistency check that I just showed you. Very valuable, right? So we have done this for 2 seasons. We are going back. And in the upcoming season, in 2-3 months, our team will go back to South Pole Station. And we're gonna change our route. We're gonna go through this South 88 route to do more observation. Particularly, we're gonna put a GPS, a geodetic grade GNSS station on the truck and monitor what's its distance to the surface of ice. In this case, we will be able to track the surface elevation of the ice along the way. That's the basic information you need to calculate the mass balance of the ice sheet. We did also left some snow sticks last year, so we're gonna do some snow accumulation. But I want to say that this type of deployment now could be done by one single group. Okay. Array is done. We started late, right? So I can go beyond 45 minutes, right? I'm trying to negotiate some more time. Now I'm gonna talk about the hidden water. Hidden water here, as you know, I'm talking about the groundwater. What do I mean by groundwater? Okay, now I'm gonna take you into more details of those seismogram. What do they mean? As I showed you, if you put a seismometer there on the ice, simple ice plus rock structure, it will give you the signal like this. Those are the signal we seismologists call them PS, PPPS. Anyway, they are just those waves that is reverberating within the ice sheet and can be recorded like this in the receiver function. If they are from the same boundary, this P converted to S and the boundary and those two faces, they are related, right? They are from the same boundary. So with some algorithm, we can convert them into depths, and those 3 signals should align themselves with each other. And then that's how we confirm that's indeed from that boundary. Do we see this kind of lining up in the same depths from our data? We do, right? This is one station somewhere here, great southwest of South Pole Station. If I line up those individual faces on the right side, I see positive, positive, and negative. That's the pattern it should be. And they line up. And the depths that was predicted by better machine. This is from single station. it has noise. But if we look at many other events, they are consistent. So which means this simple ice plus rock model works for some station. We do this convention for one phase to all stations. Now let's take a look. If this convention is right hand of the ice bottom, I should be expecting some signal from enter this place, and it should be red. I don't see a lot of red here. The only thing I see a lot of red is somewhere here, somewhere there, right? Something is interesting there. If I look at second phase, I'm expecting something red, again, for this phase, positive, along this predicted depths from better machine. Oh, now I see they are aligned, right? Maybe from first phase, they are just weak for those stations. But for these stations, this is South Pole. The station near the South Pole, the red is delayed, like the earlier plot, right? In this case, since I converted to depths, if this is a converted phase, this is about 800 meters, 5 to 800 meters, more deeper, this signal. Next signal, I should see some blue. Again, the blue is delayed, right? So instead of having a discontinuity at the base of ice sheet, this is something else. We did do some synthetic test. If we put an additional layer here, we can align the trace like this, positive, positive, negative. And many of those stations near South Pole have that pattern if it is deeper. And more significantly, for some events and some stations, this particular NNE12 over there, not just a deeper layer, I even need a layer with much lower velocity to match the signals that we would see from the data. Because the first two phases are not just positive, they become negative. You need a velocity jump from high to low at the base of the ice. And what does that mean? Well, the easiest interpretation is something else is going on beneath the ice. It have teal. Well, this is an area that you have 2.7 kilometers of ice on top of it. A teal to us basically is an unconsolidated high porosity material there, right? Then it can provide such low velocity. So we did do some calculation, treat everything like high porosity sediments. What can predict the velocity that we see beneath the ice sheet? In order to create something with a similar velocity with ice, your shear velocity has to decrease here, and this is corresponding to about 15% of porosity. And you have to put water in that high porosity rock. And in order to create a lower velocity, like this red line highlighted for that particular station, you need even higher porosity. And this is a place where we are looking at. Is it possible to have that high porosity? We are right here, Pensacola Pole Basin. There are a few rock samples that has been collected, not right here, but at the other end of the basin. The porosity measurements, indeed, they have some of the higher values. But considering the connectivity of this particular basin, if what we see is true, a big region, right? What we saw then is not just one station, it's a region with 100 kilometers at least where we see. Then it has additional ice. And does this mean there is a subglacial underground hydro system that is connected between basins? Is there, but we just haven't mapped them out yet. I put a question mark here because I only have the stations near this region. But there are a ton of nodes there, right? It's up to us whether we want to find them or not. Okay, I still have time. Okay, how do we do that? Now this leads to the third subject I want to talk about, continental scale network. I have showed you what a seismic network can record for individual events. What other networks are there in North America, right? Now what I'm going to tell you is, if we do have that network, this is what we are going to get. Now I'm going to go back and use North America as AI example. This is where I have worked a lot. And mostly I'm going to talk about results from this array. Every single broadband is deployed 70 kilometers from each other regularly throughout a continent. Show you 3 applications. This is the first one. Shear velocity averaged between 0 and 5 kilometers near the surface. What says? Red, low velocity, right? Blue, high. Okay, red and blue, this is what we show, seismologists. But if you compare this with classic sedimentary basin map, or the thickness of sediments from gravity studies, you recognize every single basin on the map to the left can be seen over here. Almost everyone. I counted unless it's off the shore where we have no station. But if it's on the continent, this is what we can map out, right? How do we do this? We just track those waves across the continent. We measure how fast they travel. We invert for the seismic model. This is what we can get. If that does not excite you, we have a lot of geologists here, right? How about, let's talk about this. What if you know seismic velocities? What else can you say in addition to the sediments? We did do an earlier study 2 years ago of using a comprehensive knowledge of shear velocity and the ratio between P and S velocity. We find that you look at the petrology. Different rocks, they are located in different places in this diagram. So if there's a way for us to place the Earth into different places, we can say which type of rock it is, right? This is geology 101 that differentiate different types of rocks. But this is more cool. Why? Because our seismic quantities is not just for the surface. We can map out the shear velocity in the middle of the crust. We can also measure the VP-VS ratio throughout the crust. This means we can get the average silica content of the crust at a continental scale. Something has happened. Okay, good. At a continental scale, right? This is, now you can visualize the chemistry of the crust in a very different angle. This is where you would expect a lot of felsic rock. This is a place where you expect a lot of mafic rock. And isn't that cool? And more importantly, since it's a 3-dimensional seismic model, all of the composition can be visualized like a transect. Now you can see how the crust material goes in from felsic to mafic to depths. Definitely this type of work has a lot of uncertainties, right? But we have done the benchmark with Xenonis. We have done the benchmark with the synthetic seismic data. A lot of my seismology colleagues are persuaded this is perhaps the way to go. And as a geologist, if we want to understand where the crust composition, the crustal evolution for a continent, this can perhaps provide a good way to move forward. And okay, we're talking about Antarctica, right? Knowing the composition, there is one more advantage. Why? Because if you look at the chemistry of the rocks, whenever you have a higher silica content, more felsic rocks, generally it has higher concentration of potassium, uranium, and naturally it would have a higher heat generation. So, if you have a 3-dimensional model of the crustal composition, you can convert that into a 3-dimensional model of heat generation. If we take this heat generation from different depths and combine that with other temperature indicators, Curie depth, surface heat conductivity, Moho temperature indicated by the seismic velocity, we can find a thermal model that can reproduce all of those measurements. We did a try. This is one of the stations. We find that, yeah, this simple conductive model can reproduce all of those measurements within their uncertainty. Actually, this is since this is North America, we also have the geothermal heat flux. So we can also use geothermal heat flux as data and try to fit for that. And for this particular place, we are not very far away. And as a result, what we can produce from this new compositional model is a new generation of thermal model of the crust for the United States, right? You have temperature from surface to Moho. What does this mean for Antarctica? Do we need a thermal model? As a geologist, I think we care about. But there's another community, glaciologists, they care about more about the geothermal heat flux. So we ask ourselves this question. What if you do not have one of those data, either geothermal heat flux or heat generation or Moho temperature, still produces thermal model? Can you predict what's a true parameter for that missing one that's not in the inversion? So we did try this for geothermal heat flux, heat generation, Moho temperature, and Curie depths. If you do not have heat generation in your input, you cannot reproduce the heat generation just by using other parameters. Because almost every other parameter is either near the surface or at the base of the crust, or at the Curie depths and the greater depths. But for geothermal heat flux, this is a parameter that we find you can miss it. But as long as you have good heat generation along the depths and good constraints on the absolute temperature from Curie depths, you can perhaps reproduce it to some accuracy. And this definitely indicates that for regions like where we care about, one can constrain the geothermal heat flux if reasonable estimates of other parameters you can get. But how do you get the heat generation at the middle crust, right? Looks like a continental scale array is needed. Okay, hopefully by now I have persuaded you the value of a large scale geophysical array can help. So, am I proposing that? Somebody has proposed that 20 years ago, right? Back in 2003 in Boulder, Colorado, a group of scientists, some of you have participated then, have gathered together and wrote this report, Antarctic Array. And in that report, people have proposed a large, bold idea like, let's cut this continent into different pieces and every country go in there and put out their own array. Well, compared with what's happening now, definitely we haven't done that yet, right? But compared with the backbone array, we have done a lot, especially for Central and West Antarctica. There, thanks to a lot of people, including the people who are sitting here, we now have a decent network in the West and Central Antarctica. But this is still different from array like that. In order to allow us to map out the sediments, to get the composition, to estimate the thermal structure. And a lot of those gaps is in East Antarctica. And that's a big region, right? 70% of East Antarctica, 7.5 million kilometers in range. And if you are thinking about every 100 kilometers, you put our array, then 750 broadband stations, right? It's 2 to 3 times larger than what we have done in the past 20 years. If you use Twin Otter, if you deploy 30 broadband stations per season, you need 250 Twin Otter seasons. I can perhaps gather all the Twin Otters on the continent. I cannot finish them within 10 years, and nobody will be able to pay me for that, right? So, it may not happen. But I want to remind you, right? For an array like this, US array, the US government spent $70 to $80 million for the EarthScope project, not including the infrastructure they invested in IRIS, the seismic center. $70 million, right? I don't think any one of us in this room has that deep pocket. As of now, who knows? You buy a ticket, buy a lottery, right? It might happen, but there might be another way. So last week, I went back, I counted how long the distance we have driven in last season. If I look at our 2 truck drivers, where they started their trip in the beginning of the season and where they ended their trip, total, they drove for about 9,300 kilometers within one season. If some of us sneak some of our station on their trucks and deploy every single broadband every 100 kilometers they drive, we are gonna get 100 broadband stations already. Well, I'm joking, there's no way for the truck to haul 100 stations with them. But if we just lower our requirement, let's say a truck team just put out 550 per team per season, and if we are lucky enough to commission 3 teams, 6 trucks, in order to get 750 stations deployed, a 5-year project is possible. And how much does that cost? If I think about how much NSF paid to charter those trucks, $25 million if we don't provide fuel, have them purchase around the continent, or even less if the national programs can provide the fuel. $25 million, that's still a deep pocket, right? Still a lot of money requires a deep pocket. But it's not unthinkable. $25 million is 100% on par to the Codex project, iStream project from the US. It's a little bit bigger than the International Thwaites Glacier project. It's only 30% of the EarthScope project, and only 5% of the 2025. Oh, okay, I have to stop, right? The machine is not happy. Of the OPP funding, and only less than 0.01% of the cost if you have to armor your shoreline before 2100. So if our array can provide a little bit more information to help us to predict the ice, the water, sea level change, to be more accurate by a little bit more, to just reduce this cost by 0.01%, we are again in this investment. So, okay, I think I'm gonna stop here. Everything I have just told was not some idea I have thought about for 10 years. A lot of caveats here, a lot of details needs to be run out. But to my very limited experience, this is not something that is not reachable anymore, right? I can imagine if 20 years ago I went into Boulder and sell this idea, people will just kick me out of the room and say, this man is crazy. But now no one is doing that to me right now. And we are also doing some groundwork, right? Since a few years ago, the community, the US community has been gathering together with Instant. We hold a workshop in 2022, another side meeting in Trieste, and another meeting last year in DC, Washington. And I just hope by the time of next IPY, we do not just have a report like that saying this is what we want. I hope by that time we already have some of our colleagues' footprint on the continent doing the real deployment. And that's all I want to say here. Thank you very much, George, for your
Okay, thank you. Very, very interesting presentation. We have time for 2 questions, if somebody has it. Over there.
It's totally a non-serious question. How did you manage to have an earthquake today before the seismology talk?
Yeah, I have it. I just cannot show it. Here, thanks to the $40 million per year investment of the U.S. government to the infrastructure, there's a institution called EarthScope. They maintain those real-time seismic sensors around the world. They maintain the data there. So whenever there's an earthquake, they have a tool in the cloud that can allow you to plot the earthquake. What I show you here is not the earthquake happened, but it was happened earlier this year in May. I did have that plot in my computer. I was trying to show that at the first 2 minutes of the talk, but I failed. I'm sorry. But I'd be happy to share with you that resource.
Okay.
Thank you. Fantastic talk. I wanted to ask about the lifetime of these small nodes. I mean, obviously they're very versatile and much more easily deployed, but do they last as long? How long might a system like this continue to operate for?
Yeah, the current system that we use, they have a battery that lasts for about 30 days, which means in order to get the data, you bury them at the beginning of the season, you have to take them out at the end of the season. There are some other sensors that can be plugged into outside external battery, a power source that might last longer. But the technology is changing all the time. So in 5 to 10 years, who knows how smaller the sensors they are and how long they last.
Okay, we thank once again Dr. Chen. Thank you very much. All right. And now I have the pleasure to present Dr. Joaquín Bastías. He's geologist from the University of Santo Tomás, Chile, and I think from another one. You can say that. Please, go ahead.
Yes. Thank you. I will try to keep it up after such a nice talk of Weinzen. Today I'm going to talk about the tectonic evolution of Antarctic Peninsula. And I will go a bit beyond back in the time, and I will try to finish as we have it today. First of all, I would like to acknowledge the several collaborators and supporters that I had throughout my PhD and postdoc research, with whom I wouldn't be able to show much of the results I'm going to be presenting today. Also in line with the Antarctic spirit, which is collaboration above all. So I have divided the presentation in two parts. First, I will be talking about the tectonic-magmatic evolution of Antarctic Peninsula. I will start with the origin. We will go from the Triassic, then throughout the presence and influence of Jurassic LIPs. Then I will finish with the cessation of the subduction during the Cenozoic. And then after, I will try to present to you how can we use Antarctic Peninsula to understand global scale problems and also more methodological approach to earth sciences. So first of all, the tectonic configuration of Antarctic Peninsula. We are somewhere here at the moment. This is the current configuration of Antarctic Peninsula located here, separating from the Southern American plate here in green and Patagonia in green is the Scotia plate, which has been nicely put throughout these days, its evolution, particularly the presentation of Leon on Wednesday, I believe. And Antarctic Peninsula has a particularity, which is that there is a small section of potentially inactive subduction of the Phoenix plate in the northern part. But for the most part, the margin is inactive. Now, Antarctic Peninsula is part of West Antarctica. And West Antarctica is formed by Antarctic Peninsula, of course, then Thurston Island, Mary Bird Land, sorry. I'm missing another the Selwood Mountains. And separating these two sections, which is West Antarctica and East Antarctica, is the Transantarctic Mountains. So what is the relevance of Antarctic Peninsula and what we should be studying it? Antarctic Peninsula is located in a key position between East Gondwana and West Gondwana throughout the Paleozoic and Mesozoic. Therefore, the paleogeographic constructions, much of the studies rely on information that we can, in the information that we can obtain from Antarctic Peninsula, so it has a key position. Now, the first interpretation of Antarctic Peninsula, which is located here as a reconstruction from Suarez, is that it was a continuation of the Mesozoic arc through the south. This position has been key to much studies in the evolution of this, of the fauna evolution of this region. For most of the geologists present here, we know that by the late Cretaceous, Antarctic Peninsula and Antarctica was looking much different. And therefore, for several species and fossils evolution, we need to, the Antarctic Peninsula might have served as a bridge, and therefore it's very important to understand the tectonic evolution also to better understand the data we have today, as well as they might be holding some key information, key fossils for the evolution of life. It is also key for the climatic reorganization throughout the Cenozoic. We know that we have a current debate about how we achieve the ice conditions that we are today challenging with the climatic crisis. But towards 34 million years, we have a significant change in CO2, atmospheric CO2, and we have a few contesting hypotheses, one of which is that the separation of Patagonia and Antarctic Peninsula, which allow the setting of the Antarctic circumpolar current, which is key as well for biodiversity and climatic conditions of Antarctica today. Therefore, we have other also hypotheses such as the collision of Asia, of India into Proto-Asia, as well as the abduction of oceanic lithosphere. But the point is that Antarctic Peninsula is then again in a key position to understand key global processes. Here I would like to show a little bit how I have been very lucky to work through most of my fieldwork in seasons throughout 2016 to last year, as well throughout the support of INACH, which has been key for my career. Also, we have benefit from very generous contributions for rock repository institutions such as the British Antarctic Survey and the Ohio State University, particularly the Polar Rock Repository, and the support of Angruno and his team. And of course, as I was mentioning before, we have collaborated with so many colleagues from different countries doing Antarctic research, and I hope to do more in the future. And my techniques, the things that I have used in my methods that I have approached to understand the studies I will be presenting today is mostly based in microanalytics. So for the most part, I use different types of mass spectrometers, which then are used to understand geochemistry, isotopic tracing, and geochronology of different compounds from whole rock. For those that are not familiar with, it's basically it's a piece of rock that is processed entirely, from mineral separates, such as apatite, zircon, and others. So what I will be showing to you today is for the most part based in microanalytic techniques and tectonic studies. So first, here I have my PhD supervisor. This is a very nicely treated a piece of outcrop in Jelcho, if I remember correctly. And I will start by talking about the origin and the ongoing debate of the origin of Antarctic Peninsula. As I was mentioning before, Antarctic Peninsula is located in this position throughout the Mesozoic, which was interpreted in the 70s, and I will say also before, based on the evidence that similar units were at both sides, in Patagonia, in southernmost Patagonia, and also in Antarctic Peninsula. So this was used to propose this model within Gondwana. Thereafter, in the 2000s, it was recognized a major shear zone, a major deformation zone in Antarctic Peninsula, which was interpreted as a suture zone between the amalgamation of two terrains. This is two continental blocks being joined together. So I will show to you today now how we try to address this problem and what we found with it. So we collect some rocks, and we have received several rocks from the institutions that I just mentioned before, and by which we study, for the most part, granular dioritic compositions of the oldest rocks of Antarctic Peninsula. So what we did is this is a bit messy with all the ages, as it's usually very difficult when you have significant amounts of data to present it clearly. But what we did is to sample the oldest rocks at both sides of the suture zone. This is what is allegedly an autochthonous and an alloctonous block. In the top, we can see the geochronology of zircons in which they yield age between 203 and 210 million years. This is late Triassic. And then we were surprised to see that the rocks at the other side of the structure were also they were overlapping, although a little bit older in the other sides of the suture zone. Now, these rocks are separated by over 300 kilometers. So we thought this is very interesting because we were actually aiming and hoping to see that they were different. Because if there are indeed alloctonous blocks involved, therefore there will be a good chance that they might yield a very different age. Something that I forgot to mention, which is very relevant, is that there is also a debate of when that suture occurred. But it has been suggested it could be from Triassic to Cretaceous. Then, I'm not going to stop in all the graph. This is geochemical data from compound rocks, so full rock, and showing different diagrams trying to organize the information using major elements, but also trace elements. But the message here is that regardless of the diagram we try to apply, we don't see a significant differences between the alloctonous and the autochthonous block. Particularly, we can see in trace elements a very similar geochemical signature, and this was very telling for us. Therefore, again, along with the age, we also have a geochemical similarity. Then we try to, with isotopic tracing, we did hafnium, strontium, and neodymium. This is a combination of mineral isotopic tracing, but also full compound isotopic tracing. And as we can see in the y-axis, the values, for the most part, they overlap. So then again, we have a similarity in both sides. And also they follow a similar trend when we compare, again, the age of particular zircons. So we analyze minerals within each rock, and we try to have a database to see if we see some sort of evolution. But at least in terms of tendency, they look similar. We also temp oxygen isotopes, and then again, we didn't saw a significant difference, although this is relevant to point out that the blue group, which is the autochthonous block, is slightly younger. Then we try to compare the data that we obtain, what is being reported for different blocks of Gondwana. So Ecuador and Colombia, Northern Andes, Peru, in Patagonia. And what we observe is that the data follow a very similar trend. Then again, suggesting that there is no significant difference between these two blocks. Hafnium isotopes, I will be showing you a few isotopic diagrams, but hafnium is quite relevant for the research I will be presenting today. And in that sense, I would like to mention that hafnium help us, and neodymium and strontium, to try to understand a bit better the sources involved in the magma. So what we do here is try to understand a little bit about the origin. So we have found that the geochemistry is similar, the isotopic tracing is similar, and the age is similar. So what we suggest that it could be the model to explain this data, it might be as following. Here, to your right, you have the positions of these magmas. And they follow a similar orientation of most of the structures and deposits, pulses of magmatism of the late Triassic when we follow the paleogeographic reconstructions. So therefore, this is again another argument in favor of that Antarctic Peninsula might have been located as a southern continuation of Antarctic Peninsula. And then, but the model has some problems, which is that we still need to accommodate some of the eastern domain. This is the autochthonous domain within some kind of deformation, which is not that clear how it could have occurred. Potentially, it could be the main suitor, but this is still to be proved. So that's about the origin. And then I would say that today the debate is a bit centered in that these two supposedly alloctonous domain are actually autochthonous or perhaps para-autochthonous within the domain of West Gondwana. Now I will go through the Jurassic and I will talk a little bit about the LIP influences. LIP is large igneous provinces, and what is the role of Antarctic Peninsula in this period, which is very important for a few reasons that I will try to explain now. During this particular period, the early Jurassic, it was marked by the late stages of this last supercontinent, Gondwana. And the magmatic province of Chonaike, which is located here, comprises Patagonia, but also the Antarctic Peninsula. Then, at the same time, we have two other LIPs, Karoo, located in southern Africa, and Ferrar, which is located in this sector of Antarctica. They have been historically associated, however, they have significant differences. One of the differences is that Karoo and Ferrar are basic, so therefore the geochemistry is very different. And while Chonaike is acidic, and more importantly, I will say, is that Karoo has lived 4 million years. I would say this has to be updated, these numbers here, for the most part. And Ferrar might have been less than 1 million years. So we have those timings, whereas in Chonaike, we have a 45 million year spread, and potentially more. So we have very different geochemistry, and then again, very different timings for these units. And why they are also important is because they have been attributed to being one of the main causes leading to the biotic crisis of the early Jurassic, which caused a 30% drop of the diversity. Then what is the mechanism or the hypothesis that sustain the development of these units? From early models to late models, they have been associated to a mantle plume. I think that this work on Navarrete nicely put it how a mantle plume was located in this sector between Africa, East Antarctica, and Patagonia, and then slowly migrated towards the margin of Patagonia and Antarctic Peninsula. But then questions are posed, which is why it gave rise to two mafic provinces, LIPs, and then why we have one acidic, and the timings. It would imply that the mantle plume generated Ferrari 1 million year or less than 1 million year, that's stationary posed in southern Africa, and then slowly migrated throughout 45 million years throughout Patagonia. And this is a rather complex evolution for a mantle plume. What we did is then again to try to separate by regions. We separate by two regions, the west margin, which is, we can think of the exterior margin, which is here in red, so therefore the margin of Patagonia and the entire Antarctic Peninsula, and the interior region, which is here in blue, in the Desert Massif, what is in Patagonia. So we are comprising the entire outcrops of the Chonaiki event. The geochemistry throughout the time, here we have Triassic, early Jurassic, and Middle Jurassic, is similar throughout the time in the case of the west margin, and the geochemical signatures suggest the involvement of mantle subduction-derived components, which is not surprising because we are on the margin and we know we have an active an arc at these locations. Then in the inland region, so therefore far from the margin, we have similar geochemical signatures, which is somewhat weird because why this magmatism will have arc subduction-related composition. Then if we inspect the isotopic tracing data, we have then again similar compositions. So we need to focus on this, on the values when we compare neodymium and strontium. This is again in whole rock. And what I want to show here is that they follow a similar tendency throughout the time, but also throughout location, at both inland and exterior. And so how can we have arc magmatism so far from the margin? This is a location of perhaps more or less 800 kilometers far from the margin. So what we suggest at the time is that it might have been related to a flat slab event. This is a shallow subduction in this section. This actually was already suggested by Navarrete, but in this particular period, which is late Triassic. And then if we observe the locations of the magmas, this is early Jurassic magmas, and then we follow the paleogeographic reconstructions, we suggest that this might be related to another event, another flat slab event. And this might have been followed by the evolution during the Middle Jurassic, which we have a slightly different configuration, and we believe that this is because we know there is some simultaneous movement towards the south with respect to Patagonia of the Antarctic Peninsula. And then finally, we have the setting of the arc in the west margin, similar to what we found today in this sector. Now, what we suggest is that by this mechanism, the mantle plume will have had a lower relevance and perhaps no relevance within the formation of these magmas. And more importantly, it will be able to explain why we have these geochemical signatures suggesting arc magmatism. I'm glad to to share with you that other people was thinking more or less of the same at the same time. So nowadays, the Chonaiki event is mostly related to a flat slab event. And we have at the moment, the debate is how this could have occurred. It's not so clear how flat slab magmatism can lead to, flat slab events can lead to arc magmatism. And we have two options currently being debated, the slab steepening. This is basically the slab gets a higher angle and retreats, or the break-off, which is that after the consumption of the oceanic lithosphere sinks into the mantle because of the change in the rheology and the thermodynamic conditions. What we are trying to do today is try to test these models, because our model actually has a significant problem, which is that flat slabs today don't generate arc magmatism. So warning. And what we're trying to do is to use thermomechanical models to emulate what could have occurred during this period and see if that is possible throughout these models, what occurs tectonically, how realistic they are. So a significant advance has to be achieved to consolidate this hypothesis. Now I will go through the last part of the evolution of the Antarctic Peninsula, which is marked by the subduction cessation. So this is a compilation that we prepared from people with Alex Burton Johnson from the BAS. And each point here is magma that has been recorded either with the geochemistry or observations in the field, sometimes isotopic compositions as well. So it's a large data set that it took quite a bit of time to build. And we have a few things to see here. First, we have color-coded by ages. So we go from 100 to up to 10, younger than 10 million years. This is the positions of the magmas, of course. And although the subduction ceased, we can still see the suture, the line of the margin. And those numbers here is the time that we estimate, and it has been estimated to be the cessation of the subduction. So we had an ongoing subduction until more or less this period. And as you can see, we have 42, 30, and 19, and so on. So towards the north, we have progressively younger ages. The graph here to the left might be looking a bit messy, so I will try to explain. This is the age of the rocks, and what we have here is the position from the arc, and as well, sorry, the age of the arc, the age of the rocks against the distance from the trench. So what we observe here is more or less the age of when this occurs. So basically we are putting in the diagram these ages here against the distances. What is very interesting is that arc magmatism ceased before subduction actually ceased. And this is somewhat perhaps counterintuitive. But Antarctic Peninsula is actually a great laboratory for understanding what occurs when subduction ceased. And then we have some magmatism that is after the subduction, so post-subduction. And we can see here that the important thing is that the subduction is currently ceased. And this occurs in this diagram is presented how this is thought to occur, which is that we have the collision of rich trench elements towards the margin, which put the Antarctic plate against the Antarctic plate as well. So the same plate at both sides. And this is the reason that why the Antarctic trench ceased. And before we have the consumption of the Phoenix plate, and this little piece here is what we can think of today of the South Shetland Islands. Now, when we observe all this data set that I just showed to you, and we analyzed their age against the distance from the trench, we see something quite particular. Older than 100 million years, we have a wide range of positions of these arc magmas. And then we have a marked migration of the arc from 100 million years, more or less, until its cessation at 20 million years. Now, the front of the arc doesn't seem to migrate, only the rear of the arc. And we think, of course, this has to be related to the fact that the subduction was progressively subducting younger and hotter oceanic lithosphere. Therefore, the cessation of the subduction also resulted in a narrowing of the arc. And then we have all the magmas that occur after the subduction. This is post-subduction magmatism, which occur at a wide range of distances from the trench. Now, if we observe the geochemistry, again, trace elements of Cenozoic, Cretaceous, Jurassic, Triassic, throughout the history of the Antarctic Peninsula, the important message here is that they don't change that much. I seem to be presenting the same diagram over again, but it's not the same. But it's just the geochemistry is similar. And it should be similar because it's the same environment, it's a subduction. So this is not really surprising. We have similar geochemistry throughout the history of the Antarctic Peninsula magmatism. But what it is interesting is that if we observe the half-unit isotopes, so then again, the half-unit isotopes help us to understand the sources involved in the formation of the magmas, against the age of these zircons. This is our analyzing zircons. So in the same zircon, we analyze the age and the isotopic composition of hafnium. And this allows us to put this data set here. Through a compilation of several different studies in the last, I would say, 10 years, maybe less than that, apologize, we have that from the Ordovician until the Triassic, more or less, the isotopic compositions follow the ancient enriched lithosphere. So therefore, we have, it suggests, it could be argued that these magmas basically roughly follow this evolution, and then only towards the Jurassic, early Cretaceous, and predominantly throughout the Cenozoic, we have a very juvenile composition. What does this mean for those that are perhaps not that familiar with these isotopes is that we can think of them have a higher influence of mantle sources, juvenile sources. Then, why is this interesting? Because we couldn't help to notice that the shift of the composition is more or less roughly similar to what we observe in the migration of the arc. We had not yet a very good hypothesis, I would say, but this is the data presented by itself. Now, the Antarctic Peninsula is an Arctic margin, or also known as Cordilleran-style systems. So we try to compare Antarctic Peninsula with other systems from other places of the world. Here we have Tibet, which is extinct active margin because after the collision of India, the subduction was suture, but we use the distance that is the suture, which is the Indus-Yarlung suture. And the graph, what is showing is the age in the data, then again the hafnium compositions, and in the x-axis, the distance from the trench. And what is being observed here and is being published and reported by several researchers is that it has control of the compositions with the distance from the trench. This is that as far is more far is from the train. Is more crustal compositions, and as we get closer to the trench, we have more juvenile composition. And this phenomena has been observed in the US Cordillera, in the southwestern states, and has been also observed in the Central Andes. The same phenomenon in which it seems that the isotopic compositions are controlled by the distance of the trench. And this has led to suggest that the current, I will say, predominant model to explain this evolution is that we have a different composition of the crust. This is the subduction, a generic subduction. In this case, is applied for southwestern US Cordillera, in which the presence of the continental mantle lithosphere is key to control the compositions of these isotopes. And this is given because as it gets closer to the trench, it's thinner, and therefore provides a lesser capacity to mix and to incorporate all continental crust, therefore conditioning the values that have been yielded when isotopes are measured in these rocks. Now, if we do the same exercise for the Antarctic Peninsula, it's not that clear. Although we have some control here, perhaps in this period, this is again distance from the trench against the isotopic compositions. We have much more noise, let's say, in the compositions. We can have rather juvenile compositions in distances quite far from the trench. Then this is what I just showed to you, in which we don't have a very good control of the isotopic compositions with the distance from the trench. But then if we do the same, we use the same data set to plot it against the age, then we have a very good constraint of more juvenile compositions with younger rocks. And then again, this is neodymium data, so it's different data set from what I showed to you with Hafnium, and it's showing the same shift towards 100 million years with more juvenile compositions. So there is a good coupling and agreement with these two isotopes systems. What we suggest is that throughout the Mesozoic, older than 100 million years, the Antarctic Peninsula was actually subducting an old oceanic lithosphere. And this old oceanic lithosphere had the capacity to dehydrate in a wider area, which allowed for these magmas to uplift and to form in the continental crust, leading to all these compositions from juvenile to more evolved that we observe. Then in the second part, from 100 million years, where we have these progressive juvenile compositions with younger ages, what occurs is that we have progressively the subduction of young oceanic lithosphere. And this young oceanic lithosphere is hotter, it's also subducted faster, and we suggest that this lead to a slab decoupling, also probably also in a dry asthenosphere, and this led to a narrow arc. And this narrow arc had this condition of forming very juvenile magmas. This is the ongoing hypothesis, and then of course, since 20 million years, what we have is the cessation of the subduction, and with the exception of this inactive or almost inactive zone in the South Shetlands. This is a very recent model, so many things has to be tested. Particularly, I would say that how we can narrow the arc is complex, but it's even more complex to explain the juvenile composition in these conditions. So significant modeling has to be achieved in order to try to consolidate these models. And now I will do the last part of the presentation, and I will try to show to you a little bit of how I have been using with some colleagues the data from Antarctic Peninsula to understand global processes. So let's look at subductions by itself. Subductions, we can simplify it to the act of oceanic lithosphere that goes under continental crust. Not necessarily, there could be also oceanic lithosphere with oceanic lithosphere, not necessarily, but the generalization could be this, in which they are very complex systems, but we can simplify to the following processes. We have, as I mentioned today, significant outputs of arc magmatism. We have subduction erosion because the act of subduction also consumes the continental crust that is being just next to the subducted slab. Therefore, we lose material through this process. We have slab dehydration. These oceanic lithospheres is of course hydrated and altered, and this allows the dehydration and basically provides all the elements for arc magmatism to be formed and lead to partial metal intersection. We have all the processes that I'm not going to discuss, but just to mention, we had delamination, perhaps also significant amounts, pieces of the crust might sink just because of the rheological transformation they experience in these conditions, and we also have continental sediment loss. So basically, we have some gains, some loss of continental crust. And there is a plethora of studies suggesting that subductions can generate continental crust, can maintain continental crust, and they can also consume it. I will try to show to you now why is this relevant. We can think of any arc magma as a mix of continental crust, slab, and mantle. And these three sources are involved in the magma. And therefore, a magma can have a composition which can be very crustal, therefore highly recycled. Could be mixed, or could be mostly mantle, which is then again capturative. Why we use the word capturative? Because in order to form continental crust, we need to capture material from the mantle. There is no other process to form it. How is it looking today? If we look today as a global scale, we can say that the generation of magma through subductions in the global estimations are more or less from 20 to 30 cubic kilometers per year. And then if we observe, we compare those with the process that lead to loss of continental crust through subduction, we have 25 to 30 cubic kilometers per year. So we can say that they broadly balance these two. So if we have to just speak of today, we should say that subductions actually do not generate continental crust at the moment if these estimations are correct. This is somewhat counterintuitive because when we observe subductions, what we observe is mountain change, volcanism, but nevertheless, these are the numbers. And I will show you a little bit more of why this is important. So this is the modern plate tectonics, what we have today in a simplified manner. And here we have the early Earth when tectonics commenced. And at this time, it's being debated of when exactly subduction starts. Because subduction is an engine of the surface of the Earth. And therefore, it's very important to understand when this occurs. Because when this occurs, we also have mixing and the formation of geochemical compositions that are similar to what we observe today. So actually, the initiation of subduction, the same phenomena that have occurred in Antarctic Peninsula, is key to understand how tectonic were set up and what is their influence. Particularly, earth scientists and geoscientists, one of the main questions I would say posed in the community is how did we achieve the current global continental mass? So early models suggested that at the beginning it was a significant amount of continental crust form, and then since has been mostly consumed. Then other models suggested that significant amount was formed early on, and then it was mostly maintained. But most models in the last 20 years, I will say, they suggest that significant amount was formed early on, but then we have a gradual but consistent growth of the continental mass. Now, this is very important for the people working here and for the geoscience community, because if this is correct, then subductions might be the mechanism to explain how this actually occurred. Then again, why is this important to understand is because the formation of the continental crust is also very important to understand the conditions that might have led to habitability in the Earth and so on. So, whoop. Okay, it's working, I'm happy. Then what we're trying to do is just to use some statistical approaches to try to fit a model in which we give these isotopic compositions, the age of the rock, and all of this allow us to have an estimation of how much proportion is from in any given magma, from the mantle, from the continental crust, and from the slab. Remember that we have a very good qualitative image of the evolution of magmas, but the idea is to provide a new tool in order to try to have a bit of a quantitative constraint in this evolution, and for which we're using basically Bayesian modeling in large data set. This is an ongoing project in an early stage, and then the idea is to use those constraints, those data, and scale it up to global data sets, and we might be able to see if subductions yield more crust-dominated magmas, or perhaps more mantle-dominated. Perhaps we're going to have a diversity of subductions zones. For example, perhaps some of them are going to be more crustal-dominant, other more mantle-dominant. In this particular graph, going back to the question of whether subduction zones generate or consume or maintain, mantle dominant will be a good argument to say subductions might be a significant contributor for the continental mass. If we observe, if we see that we lead to this kind of models is the dominant case in subduction zones, then we can then say subduction zones is not the case, and perhaps actually might be consuming continental crust through the time. Therefore, providing a global view. Finally, almost finished, I will just mention that we're going to use this data through different approaches. This is an ongoing development with colleagues from different universities, and we hope to then again use Antarctic Peninsula, what we have learned there, scale up and try to apply to global processes, and potentially maybe see something that could be useful for everybody. Thanks again for the invitation to the organization. I'm very happy to take any questions.
Okay, thank you, Joaquin, for a very nice presentation. Are there any questions from the audience? No? Okay.
Thank you, Joaquin, for very comprehensive coverage. I've got spots in front of my eyes now. You didn't concentrate on it by any manner of means, but what is your view of the original position of the Antarctic Peninsula with respect to southern Patagonia. You showed several, at least 3 different forms of relative positions.
I will try to go back. It's a bit slow because I need to go one by one. Just it will be better to discuss if we can. Okay, almost. Yes, so the relative position of Antarctic Peninsula respect to Patagonia is we have conveniently used this paleogeographic reconstruction. We know there is some debate, perhaps even some models, older models, putting it in this sector. We think that this is the evidence we have to support this particular model is because the positions of the arc magmas that we observed there. We have some deformation in this sector during this period. And what is also very interesting is that the west margin is not there. The arc is currently not in these latitudes. So we think that this could be related to this explanation. However, I'm not that happy with how this occurred exactly because we don't have so much data actually in this particular period. This is Middle Jurassic, and during the Middle Jurassic, it's quite complex to have a good data set. Perhaps it could have occurred much faster. For example, we had some gaps in the data, but we don't know. I wouldn't be able to say how good, if that's possible. Now, something that I forgot to mention, which is very important, is that we have found that the geochemistry supports this model, but geochemistry is not a sufficient condition to support this model. And this is because if you melt a rock that has been formed in an arc, for example, let's say if in the middle of Brazil was an arc, and now you melt that rock, you will have arc compositions, but that doesn't mean necessarily that it's been made by an arc. So we need to be careful with the geochemistry. That's why we really need to move into try to see if that's possible, if that occurs, and if that's possible, under which conditions. And for that, I think a very important point, which is sadly we don't have a super good constraint, is the migration of Antarctic Peninsula respect to Patagonia.
All right. Just a very short question. You mentioned that there is right now the platform near the northern peninsula is inactive, but we have an earthquake last night. So what are you thinking about that? It's active or inactive?
Yeah, the earthquake is breaking my model, but not that happy about that. Let's go back. And it's actually after, sorry. Almost there. So perhaps this is better.
One.
Yeah. So yes, we have the cessation of the subduction, but we have quite a bit of tectonism in this sector of the Antarctic Peninsula. As perhaps even in this image, you can see some kind of basin here. This is because there is an opening of the Braunfels Strait since 5 million years, and this has been extended 200 kilometers at least. So there is quite a bit of activity there, even though subduction might be inactive. So as Chileans, we relate subduction with earthquakes because we have so much of a Chilean margin. But in this sector, actually, all the tectonism, the recent tectonism, is related to the cessation of the subduction. We can think of subduction as a pressure, and when we stop that pressure, then it relaxes. But relaxation also leads to earthquakes as well.
Yeah, but the epicenter was in Drake Passage, around 250 kilometers from Fried, or from King George Island.
Where is the location, sorry?
No, the epicenter of the earthquakes last night was 250 kilometers northwest from King George Island. So it's like the blue line there.
Okay, I haven't seen we can try to take a look in the map because I don't know where it is. But so the Scotia Plate also is related. It has significant structures. Is extending, and therefore there is an ongoing deformation which leads to earthquakes as well. Okay, I thought it was close to King George. Yeah.
Okay, well, we thank once again Joaquin for
Thank you.
the
Thank you very much.
very nice presentation. Well, now we have some kind of closing ceremony. It's not like the usual closing ceremony. Yes, because after this we have coffee, and don't forget we have the last 2 sessions. But because we're now all together, I wanna say thanks to all of you. I wanna thanks to the scientific committee. They were very helpful in helping me to do all of this. And especially I want to thank Laura DeSantis. She was a very good partner for constructing all this program and all that actually you have here. Yes, from the OT4 platform, we supposedly have 22 participants. Most of them have maybe a little more from Chile, but we have 25 countries here represented. About 53% are or were women, and 47% men. But also I think about 30% were young people, students, and early career research. So I think that is very good, actually, data. At the end, let me take this out. We have 200 abstracts. Finally, here I think we have around 150 abstract presentations, either oral or poster. And I think that is very good. Remember that we have the pandemic, so this is the first one after that. So we are recovering from all dark years. And we have 8 side events that I'm sure that you enjoy and were very good for your science. The abstract book, there is a version 0 that you all probably received from the platform. And and it's version 0 because there will be another one, obviously. So if anybody have any things that need to be added or something, just let me know. The final version will be, I hope, in 1 or 2 weeks. And the idea is to have the ISBN number and also trying to get a DOI. Also, certificate for your participation will be available. We are going to send all what we can. If somebody is missing, just contact me. And regarding with the next size will be in 4 years, but I think there is procedures. We don't have any country that have been offered that, but I think that, I think Marcelo Lepe, I don't know if he's here, but he told me that there is a procedure established by SCAR. So the country that wanna host the next one have to follow that procedure in the next, I don't know, 2 years or something like that, or next year. Anyway, you probably all of you, or most of you, are going to get together for the next Open Science SCAR. I think it's next year in Norway. As I say, thank you for the scientific committee, to all of them, but also to the National Committee that was led by Director of the INACH, Dr. Gino Casassa. But personally, I want to thank all the staff from INACH. They did a very wonderful job. And that regard, I want to thank Isabel Jimenez. I don't know if she's here. I told her to be here, but she was wonderful. She helped me a lot from the beginning and all these days also. I also want to thank all the guys from the back. I think they are the B3 communication. So, you know, all these sounds and scream, everything was actually pretty good. And finally, I want to thank also people that were in the coffee break. I think they also were very nice people that serve us coffee and other stuff. So, from my part, I just want to thank you once again to all of you, and I hope that you have a safe back home. And for those that are going to stay here, just enjoy the city and the surrounding. And to close officially this, but remember, there are 2 sections after the coffee. Gino, please, your last. You want to? Oh, please.
Well, in representation of the SCAR and as head officer of the group of geoscience, I want to acknowledge you the attendance of this meeting and the reactivation of the different meeting and activities related to the geoscience. Mainly, one of the main activities that we have done in this meeting is the proposal of a new scientific research program that is that will be submitted the next year. That is now a program planning group. That is the Antarctic geological evolution. I want also to thank to the Chile to organize this good and nice meeting in this very well location near the Magallanes Strait, that is one of the bridges to the Antarctica for many countries. And this is a place that many of us, we have go and return when in our cruise or in research work in the Antarctica. I want to acknowledge the INACH and its director, Gino Casasa, that has provided all the facilities to develop this meeting in the frame of the SCAR. Also to the local organizer, that is Jorge Carrasco, that is from local organizers, and also the delegate to the geoscience that several years ago, that is Francisco Fernandoy and also Marcelo Lepe, that has proposed Chile to host this new ISAES after a bad period of pandemic period and start to have the meeting. I hope that in the future it will be, we see all in the next SCAR meeting. Thank you to all. Thank you.
Many thanks, Scar and Jesus Galindo, for his words. And just reminding you, we are three main organizers, SCAR Chile, the National Committee of SCAR, and our institute. But now I would like to, and there was a negative reply, but it's an order. People who have collaborated to come up to the a la tarima. So we're gonna see you and acknowledge you. So first of all, the ones that are closer by is INACH people. Please, if you can come here, and including Isabel, who rejected to come to the podium. So please, we don't want to delay your coffee time either, but there was really a lot of effort for many months. And Mr. Administrative Subdirector and Technical Subdirector as well. Ya, vayan. Photographers as well, por favor. Ya, dele la cámara a alguien y... No. Un minuto. Vamos todos. Okay, it seems a lot of people, but there's many more that have collaborated from our institute. We are 80 people. I don't know how many we had involved, but all the different departments. So thanks a lot for a great team, and especially Isabel was the main character, but there were so many people behind which are not here now. So thank you. Now I would very rapidly thank the productora. Ya, ahí está Paola. Por favor, adelante con la gente que tengan. The production company who was awarded the contract with the Dreams Hotel. So it's a very small group, but you put up a fantastic job. ¿No está Jaime? No. Yeah, okay. Arriba. Están los tres nomás, ¿sí? Están trabajando. There's more people from the production company. Gesto? Okay. So thank you again. Bunch of experience because they were in the Open Science last year as well in Pucón. And the University of Magallanes, we had some
slaves, students. Are there any? I can see the coordinator, Rodrigo, adelante, Villa. No? Las artesanas? No, de Universidad Magallanes, raise your hand. Is there anybody from Universidad Magallanes? Yeah, they don't want to come up to the, okay, anyway, a big applause. We had master course students and PhD students attending and helping out. Artesanas, are you here? Antarticanas, pueden venir al podio, por favor, para verlas y darle un reconocimiento. These ladies have been trained and educated in the Antarctic in our institute thanks to a project by FOSIS. ¿Qué significa FOSIS?
Ahí el experto de FOSIS nos puede...
Ah, perfecto. Adelante. Arriba.
Fondo de Solidaridad e Inversión Social. Fondo de Solidaridad e Inversión Social.
Del Ministerio de Desarrollo Social. Okay. It's our social ministry, so and you are still here. So thank you very much for all your effort and products. ¿Se me olvida algo? ¿Eso sería? Ah, APAL. And there's one from the APAL who hosted the Adelante APAL, the fantastic cocktail. It was more like a dinner at the Cabo de Hornos Hotel. When was it? Monday? So, don Jorge y Ricardo. Adelante, por favor. Adelante. So they represent 14 companies, logistic companies in Punta Arenas. It's always growing. Logistics for the science, logistics also for infrastructure and also for tourism. So thank you very much for sponsoring and attending here. We saw each other at Warsaw, so we had the biggest group in the COPNAP meeting with APAL present. Am I missing somebody? No? Okay. And as I said, I don't want to delay the coffee, but if somebody wants to share some thoughts or criticism for next ISAES meeting or whatever, welcome. Or either way, coffee is ready. So thank you very much.